Hey, what's up, Mr. Suda here. I'm going to go through some notes about igneous rocks. We looked at these notes in class. If you have any questions after I go through this, please feel free to let me know. But I'm going to boom through some introductory material about igneous rocks. So igneous rocks, how do we classify them? That's what this PowerPoint is all about. Click. All right, so igneous rocks are rocks that are formed from molten rock material when it cools and solidifies. So when lava hardens or when magma hardens, that's an igneous rock. So an igneous rock is sometimes called like a lava rock, but it's also could be a magma rock as well. So we classify, the biggest classification for igneous rocks is based on its environment. So the location where the rock solidifies into solid rock. There's two different places where the rock can solidify. It can either be an intrusive igneous rock and it solidifies inside the earth. So IN intrusive, and then IN for inside the earth. So when magma, which is lava on the inside of the earth, molten rock that's inside the earth, when it solidifies, magma when it solidifies becomes an intrusive igneous rock. Right? A plutonic rock is a rock formed deep within the earth. This is an example of a pluton down here breaking off from a magmatic body. And when this magma cools, it becomes igneous rock. The other side is an extrusive igneous rock. Think about extrusive, like an exoskeleton for a bug is on the outside of the bug. Extrusive or EX for exiting, it's going out of somewhere. Extrusive igneous rock is on the outside of the earth. So when lava's on or a magma reaches the outside of the earth, we call it lava now. So when lava solidifies outside of the earth, that molten rock, it becomes an extrusive igneous rock. And oftentimes these rocks are sent out by a volcano or some smaller type of opening on the Earth's surface. So those two types of rocks, extrusive and intrusive. On the left we have an extrusive igneous rock, and on the right we have an intrusive igneous rock. The biggest way or the best way to tell the difference between an extrusive rock and an intrusive rock is based on the size of the crystals. So for example, for this extrusive rock here, this is rhyolite. The crystal grains are so small that you would need a microscope in order to see them. There's some very tiny ones here, but for the majority of the rock, it's all this big pink blob here. And this happens as the lava on the outside of the earth, as it cools really, really, really fast, going from being really hot inside the earth to much colder on the earth's surface. It causes the lava to cool very fast. And because of that, there's not a lot of time for the crystals to grow and develop. So we get left with no crystals. To contrast, on the right side, we have an intrusive igneous rock with all these crystals all over, these nice and large crystals. The intrusive rock cools on the inside of the earth where it's still relatively hot, and it takes a long time for it to cool down still. So when this rock cools down inside the earth, because it takes a long time to cool down, there's a lot of time for these crystals to grow into these nice large shapes. So extrusive, no crystals. Intrusive, has crystals. Extrusive, cools fast. Intrusive, cools very slowly. So next we have crystal size too, which I kind of just talked about a little bit. Crystal size refers to the actual measurement of the individual crystals or the aggregate. Aggregate are the pieces that are inside of the matrix, which is the majority of the rock. So like over here, the pink stuff would be the matrix, and the little black pieces would be the aggregate. So crystal size is an important feature here. It can help us determine a few different things, but really helps us to classify the rocks further into other categories, whether they're coarse, they're very coarse, glassy, or fine. So the longer cooler times, the rocks with longer cooling times, the intrusive igneous rocks, are generally coarse to very coarse, and the rocks with shorter cooling times, because they don't have any time for the crystals to glow, are generally called glassy or fine. So this is page 6 of the Earth Science Reference Table. This is what we're going to be using to identify igneous rocks. There's a bunch of different things on here. We also have whether it's intrusive or extrusive. We have whether it's glassy, fine, coarse, or very coarse. For textures, we have whether it's vesicular or non-vesicular. We have all of the names of the rocks in here. And we have crystal size also listed. And down here below, we have the chemical composition of the rocks themselves, and I'll talk more about this in a little bit. So for igneous rocks, the texture or appearance of the appearance or character of the rock is called the texture. A vesicular texture is when there's gas pockets all over the mineral itself. So what happened when this is an extrusive rock. We can tell it's extrusive because there are no crystals. As this extrusive igneous rock was shot out of a volcano, it cooled so fast and so rapidly that it solidified with no crystals, but also there was gas trapped inside of this mineral here. I'm sorry, none of this mineral, of this rock. As the gas was there was gas inside the lava, and as the gas tried to escape the lava as it was hardening, it escaped and it left us with these gas pockets here. So these bubble marks, where it looks like there could have been like a little bubble inside, these gas pockets are telling us that gas escaped from this rock when it was solidifying. So this is a vesicular texture. These are vesicles here. Also, we can have a glassy texture. So when lava is put into water, quenched very rapidly, and it cools very quickly, crystallization can occur, and that gives us a glassy texture. So few or no crystals. So on the top left, we have scoria. On the bottom right, we have obsidian. Both of these rocks we would call a glassy texture because they have few or no crystals inside of them. Right? Both of them cooled very, very fast. And we can see that over here. Here's a glassy texture on the right. Glassy means non-crystalline, so there's no crystals inside of it. They can be non-vesicular. In the case of obsidian, there's no vesicles on here. It's non-vesicular. Or it can have gas pockets on it, which means it would be vesicular, like scoria. So all of these rocks here are all glassy. Obsidian, pumice, basaltic glass, scoria are all glassy textured. Next we have color. So these rocks can be either light or dark colored. On the left side, it's a light colored rock. On the right side is a dark colored rock. The rocks that are on the left side, the light colored ones, are going to be called felsic igneous rocks. And the rocks that are dark on the right side are going to be called mafic igneous rocks. So if you look on the earth science reference table, it'll show you that the lighter colored rocks are to the left. So rhyolite, granite, pegmatite, these rocks on the left are lighter in color, and these rocks on the right, gabbro, diabase, basalt, all these are darker in color. They're also going to be more felsic towards this side, and they're going to be more mafic towards this side. The density will be lower over here, so it'll be lighter on the left side. The density will be heavier on the right side. So density, if you remember from the beginning there, is the ratio of the mass to volume of the rock based on its composition. So it's mass divided by its volume. And it can be either lower or higher. Lower meaning the density is low, which if it falls below 1, it could like float, for instance, or higher if it has a very high density. For example, lead has a very high density. That's what you would call something being like heavy. When you describe something as heavy compared to like a 6-foot block of styrofoam is not very heavy, but a 6-foot block of lead is very heavy. The styrofoam has a lower density than the lead does. And this is on the science reference table, no memorization required. So the ones that are on the left side, as you move towards the left, they become lower in density, and as you move towards the right, they become higher in density. So dunite is a very dense rock. Next we have composition. So it's the mixture of the materials found inside the rock. So rocks can be made up of lots of different minerals, and even the same types of rock can also be made of different minerals. We'll talk about that in a little bit. So there's two big distinctions of igneous rocks in terms of their chemical composition. We have felsic rocks, which are light colored and have a high aluminum and silicon content. And we have mafic rocks, which are dark colored that have a high iron and magnesium content. Do you have to memorize that? Absolutely not. It's right inside the reference table. So on the left side, we have the felsic rocks, and it tells me that they're rich in silicon and aluminum. And on the right side, we have the rocks which are more mafic. They're rich in iron and magnesium. So I'm not going to play this video out now, but I will leave it inside this notes file that I'm going to post. This is a video from Mr. Smith, who also teaches earth science here at Valley Central, and he does a really good job overviewing the different rocks that are inside of this chart. So I'll leave this inside of the notes file, and you can play the video through that. And if you have any questions, please let me know. All right, lastly here we have the mineral composition, so the minerals that are making up the different percentages of the rock. So, for example, we have quartz here on the left, potassium, feldspar, plagioclase feldspar, biotite, amphibole, pyroxene, and olivine. These are the minerals, or these are the largest percentage of minerals that make up igneous rocks. Some igneous rocks have different minerals than just these ones, but these are the most common minerals which form igneous rocks. So you're going to get a question like this. It says, which intrusive igneous rock would be composed of approximately 60% pyroxene, 25% plagioclase feldspar, 10% olivine, and 5% amphibole? So to answer a question like that, I would go to my igneous rock classification here, and I'm going to see if I can use some of the tools here. And I'm going to eliminate options as I go through. So the first thing that I should do is take a look here. So we have 60% pyroxene, 25% plagioclase feldspar, 10% olivine, 5% amphibole. All right, so I'm going to write that down real quick. So 60% pyroxene, 25% plagioclase feldspar, 10% olivine, and then 5% amphibole. All right, so let's go back to the next page. So this is what you would use to answer a question like that. So I'm just going to write down what we have to work with. So we have 60% for pyroxene, pyrox. And I'm just going to abbreviate. Actually, no, I'll write the whole thing. Might as well. There's 60% pyroxene, 25% plagioclase feldspar. I'm just going to write plagioclase. Place. There we go. 10% olivine, and then 5% amphibole. Amphibole. All right. So now how do I eliminate options? So I have all these different rocks to choose from. The different rocks here correspond to these different parts of the chart. So if I can draw a line here, this column, or each of the columns, belongs to these dashed columns down here. So for example, I'm going to try to draw this as straight as I can. One more. So for example, pegmatite, granite, rhyolite, vesicular rhyolite, pumice, and then obsidian sometimes can all have the same chemical composition. The difference in between them is the cooling time. So pegmatite takes a very long time to grow. It has very large, 10 millimeters or larger, very large crystals in it. It takes a very long time to grow. But it's made up of the same stuff as rhyolite. The difference being rhyolite cools, it's an extrusive igneous rock, cools much, much faster than pegmatite. So there's no time for those large crystals to grow. But if you had a lava with the chemical composition of potassium feldspar, quartz, plagioclase feldspar, biotite, and amphibole, and you let that lava, which would otherwise become rhyolite, cool for a long time inside the earth, it could become granite or pegmatite. So all of these rocks can have the same chemical composition, but they look different because of how long it took them to cool. So what I can do now is I'm looking for a rock that fits all these descriptions. So we're looking for one that has pyroxene, plagioclase feldspar, 10% olivine, 5% amphibole. So let's eliminate some options here. So the first thing I need to do is I can go down to the bottom of this chart here, and I'm looking for pyroxene. So on the left side here, I don't see any pyroxene. There's pyroxene over here. So there's 1, 2, 3 columns that have pyroxene in it. I'm going to eliminate all the options that don't have pyroxene. So this side didn't have any pyroxene in it, so it can't be any of these rocks above. It can't be dunite, because dunite is composed just of olivine. And actually, this column 2, diorite and andesite, does have a teeny tiny bit of pyroxene in it. So you might think that it could be that option, but it's telling us that it's 60% pyroxene, this unknown rock. And 60%, here's 0. 60% is going to be somewhere up here. And it's not nearly that tall, this amount of pyroxene. So it can't be this column. I can cross those out. So now I'm down to it here. I know it's 60% pyroxene, 25% plagioclase feldspar, 10% olivine, and 5% amphibole. And that also eliminates peridotite here, because peridotite is just olivine and pyroxene. So now I've eliminated a lot of my options here. Now I'm down to 1, 2, 3, 4, 5, 6 options to choose from, which is much better odds than anything else that I would have been left with to start. Almost, I'm not sure how many rocks here, I didn't count, but much more than 6, more than double. So I've gotten really good odds here now, I'm guessing. So, but there's one more piece that we needed. If I go back, hopefully it'll save my drawing here. Good, it does. So the giveaway here for us, aside from that, so I know that I'm in this column now, and my giveaway here, it says which intrusive igneous rock is, and then made of that chemical composition. There's only 2 rocks here, which could be classified as igneous, intrusive. So all these extrusive rocks, so basaltic glass, scoria, basalt, can't be any of those. And also diabase can sometimes be extrusive or intrusive. It's kind of on the borderline, but because it's not exclusively intrusive, I'm going to cross that one out. And then I'm left with gabbro is my answer. All right, so gabbro is an intrusive igneous rock that could be made of 60% pyroxene, 25% plagioclase feldspar, 10% olivine, and then 5% amphibole. Right? And sometimes it could be made of more or less pyroxene. So on the left side here, anything that falls within this range could be gabbro. Right? So on the left side here, if you had a gabbro, you could have a gabbro that's made of up of a lot of plagioclase feldspar. So it could be almost more than 50% plagioclase feldspar, a good chunk of pyroxene, and then amphibole. Or I could have olivine, which is more towards the right side, where it's a little bit of plagioclase feldspar, mostly pyroxene, and then a chunk of olivine, and then a little bit of amphibole. So I could have a gabbro where there is olivine, and on the left side I could have a gabbro where there's no olivine. And this is the reason for granite colored countertops being different colors. So for example here, I've got a bunch of different colors for this granite here. Sometimes granite could be like a reddish color, it could be a bluish color, it could be green, it could be brown. All of these could be granite. For sure, they could all definitely be granite. But what makes them different is the amount of each mineral that they have, because the minerals themselves are different colors. So for example, if you have a light colored granite countertop here, for example like this one, there's not a lot of black pieces in it, which tells me that this granite probably doesn't have a lot of biotite in it. So if I go back to my chart here, that's not the right one, this one here. If I go back to my chart, I could have a granite that has a lot of potassium feldspar, a little bit of quartz, a little bit of plagioclase feldspar, a little bit of biotite, and then a little bit of amphibole. So potassium feldspar is pink, or it could be up to white. But if you're going to get a nice pinkish granite countertop, it means it probably has a lot of potassium feldspar in it. And if you go to the right, if you have like a really dark colored granite countertop, it probably doesn't have a lot of potassium feldspar in it, so it's probably on the right side here. A teeny bit of potassium feldspar, still a lot of quartz, so there could be some clear minerals in it. Could be whitish, could be clear. A lot of plagioclase feldspar here, so it could be white, but you're not going to get that pink color. And then lastly, we have biotite, which is this black color here, which tells us that we could have these black crystals in it, and amphibole as well as black. So your blackest garnets are going to be towards the right side here, and your pinkest granites would be towards the left side here, and then everything else would fall in between. So granite, is made up of all these different minerals, but they can vary in the amount of minerals that it has that make up that specific rock. So pegmatite and granite could have the same chemical composition. They could be different based on their cooling times, but also you could have a granite on the left side, or you could have the granite on the right side of this column, and it would still be granite as long as it falls within these boundaries here. All right, that's going to wrap it up for igneous rocks. I know that was a really long one. If you have any questions as you're watching this or afterwards, please feel free to email or message me. Other than that, I hope you have a great day wherever you are, and I will see you when I see you. Bye.